If you're a .NET or Java developer, you've probably heard it 1,000 times. You need to learn system design. But every time you try, it feels like diving into chaos. Load balancers, proxies, microservices, queues, consistency models. And you're left wondering, where do I even start? Here's the truth. Most developers, even senior ones, struggle with system design not because they're not smart enough, but because nobody ever showed them the path. In this video, I'm going to change that. You're going to see what system design really means for a back-end developer. Not abstract theory, but how real systems are built, scaled, and kept alive in production. By the end, you'll finally understand how all the pieces fit together, from API to databases, caching, messaging systems, and beyond. This is your first step to thinking like an architect. Welcome to the next level of your career. Welcome to system design. Let's start with the foundation of every modern application, the client-server architecture. Think about it like this. On one side, you have the client. It could be your web browser, a mobile app, or even a desktop program. The client's job is simple. It asks for something. It might want to display a list of products, send a message, update a profile, or delete an item. On the other side, you have the server. That's where the logic, processing, and data live. The server listens to those incoming requests, processes them, maybe talks to a database, applies some business logic, and then sends back a response. This back-and-forth communication usually happens over the internet using protocols like HTTP or HTTPS. The client doesn't need to know how the server works internally. It just knows that when it asks, it gets an answer. That separation between what the user sees and what the system does is what allows us to build scalable and maintainable applications. This architecture is the core building block of system design. Once you understand this flow, you can start layering concepts like APIs, load balancers, caching, and microservices, piece by piece, building toward real-world scalable systems. Now that we understand the basic client-server model, let's take it one step further. In small applications, a single server might handle everything: business logic, database operations, and even static files. But as systems grow, that approach quickly becomes a bottleneck. That's where the three-tier architecture comes in, a foundational concept in system design. We split our system into 3 layers. The presentation layer. This is the client, your web app, mobile app, or desktop interface that users interact with. The application layer. This is the middle layer, the server or backend where your business logic lives. It handles requests, applies rules, communicates with databases, and coordinates other services. The data layer. This is where information is stored, usually in a database like SQL Server, PostgreSQL, or MongoDB. When the client sends a request, let's say, "Show me my orders," the request goes to the application layer. The backend fetches that data from the database, processes it, and returns a clean response to the client. This separation makes systems more scalable and maintainable. Each layer has its own responsibility, and that's the first real step toward thinking in distributed systems. In real-world architectures, these layers might live on completely different servers, or even in different regions across the cloud. Yet they all work together seamlessly. And from here, we can start exploring the next big evolution, scaling. How do we handle thousands or millions of users, all sending requests at the same time? That's where concepts like load balancers, caching, and microservices start to shine. When you send a request to a server, it doesn't always go straight there. In many systems, there's something standing in between, a quiet, invisible gatekeeper called a reverse proxy. Think of it like the receptionist at the front desk of a massive building. You walk in and say what you need, but you don't go directly into the offices yourself. The receptionist decides where to send you and sometimes whether to let you in at all. The reverse proxy does the same thing for your requests. When your browser or app sends a request, the proxy receives it first. It then decides which server or which copy of the server should handle it. This makes your system more secure and efficient. The proxy hides your real identity and location from the servers, protecting privacy. It can also balance traffic, cache responses, and even block suspicious requests before they ever reach your backend. So, even though it feels like your request goes straight to the server, it actually passes through a smart traffic controller, silently managing and optimizing the flow of millions of requests every second. Tools like Nginx, HA Proxy, or YARP in .NET are common examples of reverse proxies, and they're a key piece of almost every large-scale architecture today. One of the biggest causes of delay in any system isn't your code, it's distance. Imagine this. Your server is hosted in America, but your user is sitting in China. When that user sends a request, the data has to travel halfway across the planet. And then, the response has to travel all the way back. That round trip creates what we call latency, the time it takes for a request to reach the server and come back. And no matter how fast your code is, you can't escape the laws of physics. The farther the distance, the longer it takes for data to move. So how do big companies like Netflix, Google, or Amazon solve this? They deploy their servers all over the world, in multiple data centers or regions. That way, when a user connects, they're automatically routed to the nearest server. Less distance means faster response times, better performance, and a smoother experience for users everywhere. This global setup is the foundation of content delivery networks, or CDN, systems built to bring your content closer to your users. And that's how modern system design breaks the limits of geography, by distributing infrastructure across the world. Now, let's talk about one of the most important pieces of modern system design, the API. Think of an API as a middleman, a bridge between the client and the server. When your application wants to access data, update a record, or delete something from the database, it doesn't talk to the database directly. Instead, it goes through the API. The API receives the request, processes it, often by communicating with other services or databases, and then sends back a response, usually in formats like JSON or XML. This makes communication structured, secure, and consistent. There are many types of API, but the two most popular are REST and GraphQL. REST APIs are based on simple HTTP methods like GET, POST, PUT, and DELETE, perfect for most web and mobile applications. GraphQL, on the other hand, gives the client more control, allowing it to request exactly the data it needs. Nothing more, nothing less. APIs are what make modern applications flexible and connected. They're the communication language of the internet. Without API, systems couldn't talk to each other and the web as we know it wouldn't exist. Let's take a closer look at a REST API, one of the most common ways clients and servers communicate today. REST defines a structured way for applications to exchange data over HTTP. In a REST API, the client sends an HTTP request. For example, a GET request to retrieve data, or a POST request to create something new. The server receives that request, processes it, and sends back a structured response, usually in JSON format. One of the most important principles of REST is that it's stateless. That means every request is independent. The server doesn't remember who you are or what you did before. Each request must contain all the information needed for the server to understand and process it. This design makes REST APIs simple, scalable, and easy to cache. Perfect for distributed systems where millions of requests come from different clients around the world. In short, REST defines how clients and servers talk to each other, cleanly, consistently, and without keeping track of session state. Now that we understand REST, let's compare it with another popular technology, GraphQL. Both REST and GraphQL are ways for clients and servers to communicate, but they follow different philosophies. In a REST API, data is divided into multiple endpoints. For example, users, users1, orders, products, and so on. Each endpoint returns a fixed structure of data. If your app needs extra information, it often has to make multiple requests. One for users, another for orders, another for products. GraphQL changes that. Instead of multiple endpoints, there's only one, a single entry point where the client can specify exactly what data it needs. Need just the user's name and their last 3 orders? You can ask for that, and the server will send back only that data, nothing more, nothing less. This makes GraphQL more efficient when working with complex front-ends or mobile apps that care about bandwidth and speed. However, REST is simpler, easier to cache, and works perfectly for most traditional backend systems. In short, RESR, multiple endpoints, fixed data structure, stateless and cache-friendly. GraphQL, single endpoint, flexible data queries, efficient but more complex. Both have their place, and as a system designer, understanding when to use which is a key step toward thinking like an architect. Now, when the client makes a request to retrieve, create, or update data, it raises an important question. Where is all that data actually stored? For small applications, we could keep data in memory, or maybe in a simple file. But modern systems handle massive amounts of information. Millions of users, transactions, and events every second. That's why we need dedicated servers to store and manage data efficiently. We call them databases. A database ensures your data is safe, structured, and accessible whenever you need it. But not all databases are the same. There are 2 main families, SQL and NoSQL. SQL databases, like SQL Server, MySQL, or PostgreSQL, store data in tables with rows and columns. They follow a strict structure called a schema, and they use SQL language to query data. SQL databases are great when your data has clear relationships, like customers, orders, and products, and you need transactions and data integrity. NoSQL databases, on the other hand, are more flexible. They were built for scalability and performance when dealing with unstructured or rapidly changing data. NoSQL isn't one single type. It's a family that includes key value stores like Redis or DynamoDB, perfect for caching or fast lookups. Document databases like MongoDB, great for storing JSON-like data structures that evolve over time. Column databases like Cassandra or HBase, optimized for analytics and handling huge volumes of data. Graph databases like Neo4j, designed to model relationships like social networks or recommendation engines. So which one should you use? If your data is structured and consistency matters, go with SQL. If your data is large, flexible, or distributed across many servers, NoSQL might be your best choice. In real-world systems, most companies actually use both SQL for critical business data and NoSQL for scalability and speed. Understanding when and how to mix them is one of the key steps in mastering system design. Today, most modern applications use a mix of SQL and NoSQL databases, relational for structured data, and NoSQL for flexibility and performance. But as the number of users grows, even the best database can start slowing down. Requests take longer. Latency increases. One simple way to fix that is to upgrade your server. Add more CPU, more RAM, more storage. This approach is called vertical scaling, or scaling up. But there's a limit. You can't keep upgrading forever. Hardware becomes more expensive, upgrades mean downtime, and one machine can only go so far. That's where horizontal scaling comes in. Instead of one giant server doing all the work, we use many smaller servers working together. Think of it like adding more lanes to a busy highway. Instead of forcing all the cars into one lane, you spread the traffic evenly across several. Each server handles a portion of the load, and a load balancer distributes incoming requests between them. This approach makes your system more scalable, more resilient, and easier to maintain. If one server goes down, others can take over. If traffic doubles, you simply add more servers to the cluster. This is the foundation of cloud scalability, systems that grow horizontally to meet user demand, instead of relying on one machine to do it all. Using horizontal scaling brings huge benefits: more servers, more power, and more reliability. But it also creates a new challenge. When a user sends a request, how do they know which server to connect to? That's where the load balancer comes in. Think of it as the traffic controller of your entire system. Every incoming request from a client first goes to the load balancer. The load balancer then decides which server should handle that request and forwards it there. If one server crashes, the load balancer instantly detects it and redirects all new requests to the healthy servers, keeping your system online and your users happy. Under the hood, load balancers use different algorithms to decide where to send traffic. Round robin sends each new request to the next server in a rotating order. Least connections picks the server that's currently handling the fewest active requests. IP hashing sends requests from the same user to the same server based on their IP address. These strategies help distribute load evenly, prevent overloads, and ensure that every user gets a fast and stable experience. Whether it's Nginx, HA proxy, or AWS Elastic Load Balancer, this single component is what keeps large-scale systems reliable, balanced, and always available. So far, we've talked about scaling our servers and balancing user traffic. But there's one part of the system that often becomes the biggest bottleneck: the database. No matter how many servers you add, if all of them depend on a single database, that database will eventually struggle to handle the load. This is where database replication comes in. Instead of having just one database, we create multiple copies, also called replicas. Typically, there's one main database, known as the primary or master, which handles all the right operations like insert, update, and delete. Then we have one or more replica databases, sometimes called read replicas, that receive a continuous stream of updates from the primary. These replicas handle read requests, fetching data for users, while the primary focuses on processing writes. This setup helps reduce pressure on the main database, improves performance, and increases availability. If one replica fails, others can still serve read traffic. And in some systems, if the primary crashes, a replica can even be promoted to become the new primary, keeping the system online. Database replication is at the heart of every large-scale architecture. It's how we make sure our data is fast, available, and reliable around the world. As our system keeps growing, even with replication, a single database can still hit its limits. Too much data, too many writes, too much traffic. When one machine can't store or process all that information anymore, we need a smarter solution. And that's where database sharding comes in. Think of sharding as splitting your data into smaller, more manageable pieces, called shards. Instead of storing everything in one massive database, we divide the data across multiple databases, each one responsible for just a portion of it. For example, users with IDs from 1 to 1 million could be stored in shard 1, users from 1 million to 2 million in shard 2.2, and so on. When a request comes in, the application knows exactly which shard to talk to, based on that user's ID or another key. This allows us to scale horizontally. We can keep adding shards as our data grows instead of overloading a single database. It's like splitting a giant warehouse into smaller specialized warehouses, each handling its own region. The result? Faster queries, less contention, and virtually unlimited scalability. Of course, sharding adds complexity. Managing distributed data, handling joins, and ensuring consistency become harder. But it's one of the most powerful strategies used by companies like Facebook, YouTube, and Twitter to handle billions of records efficiently. Sharding isn't just a database trick, it's a mindset shift. Instead of one system doing it all, you design for many systems working together seamlessly. Even with replication and sharding, constantly reading data from a database can still be slow, especially when millions of users request the same information over and over again. That's where caching comes in. Caching means storing frequently accessed data in a temporary memory store, like Redis or Memcached, so that future requests can be served instantly without hitting the database. Imagine you're checking your profile page. The first time you load it, the system fetches your data from the database and stores a copy in the cache. The next time you open the same page, the data comes straight from memory. No database call, no delay. This pattern is called cache aside or lazy loading. Here's how it works. The application first checks the cache. If the data is found, it's a cache hit and it's returned immediately. If not found, a cache miss, the app queries the database, returns the data to the user, and saves it in the cache for next time. But cached data can't live forever. What if the underlying data changes? That's where TTL, time to live, comes in. TTL defines how long an item should stay in the cache before it expires. For example, if a cached record has a TTL of 5 minutes, it will automatically be removed or refreshed after that time. This ensures that your cache stays fast, but also up to date with the latest data. Caching is one of the simplest yet most powerful ways to improve performance. It reduces database load, cuts response times, and delivers that instant, snappy experience users love. Before we talk about advanced scaling, let's take a step back to one of the fundamentals of database design: normalization. Normalization is all about organizing your data efficiently, making sure it's clean, consistent, and easy to maintain. In simple terms, normalization means breaking large, complex tables into smaller, related ones, so that every piece of information is stored only once. Why is this important? Because when data is duplicated, you run into big problems: inconsistencies, wasted space, and complicated updates. For example, imagine a table that stores user information along with their order details. If a user changes their email, you'd have to update it in multiple rows, and it's easy to miss one. With normalization, you'd separate that into two tables: a users table that stores user data, and an orders table that references the user by an ID. This makes updates simpler and data more reliable. There are several normal forms, or levels of normalization, each enforcing stricter rules, like eliminating duplicate columns, removing partial dependencies, and ensuring that each field depends only on the primary key. The goal is to reduce redundancy and improve integrity. But there's a balance. Too much normalization can slow down reads because data gets spread across many tables, requiring complex joins. That's why, in large-scale systems, developers often use a mix of normalized and denormalized structures: normalized for data integrity and denormalized for performance. Understanding normalization is the first step toward designing databases that are both efficient and reliable. Now imagine you're building a platform like Netflix or Spotify, and you need to store large files like videos, songs, or images. Traditional databases aren't designed for that. They're great for structured data, but not for huge binary files. That's where Blob storage comes in. Blob stands for Binary Large Object. It's a type of storage optimized for saving massive unstructured files, things like media, backups, or documents. Instead of storing the file itself in the database, you store it in Blob storage and keep just the file's URL or metadata in your database. The advantages? It's scalable, cost-effective, and fast for large files. Services like Azure Blob Storage, AWS S3, or Google Cloud Storage can handle terabytes or even petabytes of data easily. The downside? Accessing files isn't as instant as querying a database, and managing permissions or versioning can be more complex. But for storing large, unstructured data at scale, Blob storage is the way to go. Traditionally, many applications were built using a monolithic architecture. Everything packaged together in one big codebase: the user interface, the business logic, and the database access. This works fine for small projects, but once your app grows, with millions of users, problems start to appear. Security becomes harder to manage, latency increases, deployments take longer, and the entire system struggles to handle the load. That's why most modern companies are moving toward microservices architecture. In this model, the system is divided into smaller, independent services, each one responsible for a single task, like authentication, payments, or user management. These services communicate with each other using Kafka, RabbitMQ, or REST API. Each microservice can be deployed, scaled, and updated independently, and even have its own database, giving teams more flexibility and reliability. If one service fails, the others keep running. It's a completely different way of thinking. Building systems as a collection of small, focused components that work together to create something much bigger. In a microservices architecture, different services often need to talk to each other, but not always in real time. That's where message queues come in. A message queue acts like a middleman between services. One service, called the producer, sends messages. For example, a new order was created. Another service, called the consumer, receives and processes those messages. Maybe it sends a confirmation email or updates inventory. This setup makes the system asynchronous and resilient. Even if one service is slow or temporarily down, messages wait safely in the queue until they're processed. Tools like RabbitMQ, Kafka, or Azure Service Bus are commonly used for this. Message queues are the backbone of reliable communication in large distributed systems.